Hello everyone. So today we are here to discuss on the topic geometrical and optical isomers for coordination compounds. So let us just discuss one by one geometrical isomers in tetrahedral complexes. Now if you see the tetrahedral complex, you will come to know that all the angles in it are 109 degree and 28 minutes. And if you flip this up, you will find that also angle in 109 degree and 28 minutes, which means that all the angles are of same degrees. Okay, now if you rotate these ligands, or if you displace these ligands by one another, you will find no change in the structure, which refers that there is no geometrical isomers formed in tetrahedral complexes. Okay, now if you discuss these square planar structures like Ma4, you will come to know that A are the type of ligands, same type of ligands are getting attached to central metal atom. Now if you rotate A, you will find no change in the structure, and if there is no change in the structure, there is no isomer formed. Okay, now this is the another type of square planar structure, Ma3b. Okay, now if you rotate A with B, see, there is no reason to change A with A, because clearly we can see that if you will change A with A, you will find no change in the structure. Okay, so these are different. Let us just try with this, that if these are different and we just displace one another, then what will be the change in the structure? Okay, we displace this, we write the B ligand at the place of A, and similarly A ligand with at the place of B. Okay, now even if we change the position of A and B, you can see that opposite to A is A, and here opposite to A is A, no change. Okay, opposite to A is B, and here opposite to A is B, which means no change in the structure formed. Okay, now if you want to see the number of geometrical isomers, you can just make different arrangements of the ligands. Okay, now with this A3B, we made this. Okay, and if we interchange the ligand, we found that there is no change in the structure, which means that there is no geometrical isomer formed of this Ma3b type square planar structure. Okay, the another type is Ma2b2. Okay, now the possible arrangements of these ligands are AABB, AB, AB. Okay, so these number of possible arrangements tell us the number of geometrical isomers formed for a structure. Okay, so this is central metal atom, and we attach the ligand to it. Okay, now you can see opposite to A is A, and here opposite to A is B, which means these are different two structures. Okay, so these are the two isomers, two geometrical isomers formed for this structure. Okay, and this is MABCD type structure. And similarly, if we made the arrangement of ligand, we found three geometrical isomers formed for this structure. Now let me just explain you one thing, that this is a general formula. Ma4 is a general formula. Okay, so if you make it in more specific way, you will come to know that this is particularly a compound that is getting attached in this way. This is particularly a compound that is getting attached in this way. This is a compound that is getting attached in one another way, or all the ligands are same, in which the arrangement will be same. Okay, the position of A and B will be displaced by C and D at two places. Okay, now let me just give you some examples like NiCN4. Okay, I am just making it more specific to you, that you understand all the general terms at the end. Okay, I don't think that I need to give all the examples. You can find yourself, these are just general forms, and you have to make the same type of structure in all these type of general forms. Okay, now if you see this Ma2B2. Okay, so PT NH3 twice Cl2. This is another type of square planar ligand. Okay, Now let us start with optical isomers. This is all about geometrical isomers. Hope you understood the geometrical isomers completely. Okay, let us just start with optical isomerism. So, firstly, just discuss the general terms that are getting used in optical isomers. See, this is a plain polarized light. Okay, if it is passing through a solution, if there are two cases, either the light will pass same as it is the light we initially passed through the solution, and either the light will bend, and the bending of light or passing straight of light depends on the nature of the solution. Okay, so when the light passes as it is, there is no change in the passage of light, you can say that the coordination compound is optically inactive. Which coordination compounds? The coordination compounds that of which the solution we are taking. Okay, that is optically inactive. Optically inactive. Okay, optically inactive is obviously a new term, so we will discuss it later on. Okay, and if it bends the light, if the solution bends the light, then the solution is optically active. Okay, now if the solution is optically inactive, there will be no isomers formed, and if the solution is optically active, then two types of isomers will be formed: levorotatory and dextrorotatory. Okay, so we will discuss these terms first later on. Firstly, we have to discuss what does optically active and optically inactive means. Okay, so see, this is a structure, Ma4 structure. Okay, if we see its mirror image, we find that there is no change in the structure. Okay, and if there is no change in the structure, we can say that no optical activity is done by this compound or this coordination compound. Okay, and if we see MACD type structure, MABCD type structure, we will come to know that when we take its mirror image, we get another type of structure which is not exactly similar to C. See, the ligands are same. Okay, the structure is almost same, but the arrangement of ligands varies. Okay, so what happens is, the in mirror image we know that lateral inversion is formed, and if the ligands are different, then only we can see that lateral inversion, because see, here the ligands were of same type, A4 type. Okay, and we could not see any type of arrangement change after the optical activity, so we simply say that there is no optical activity done in this structure. Okay, and if we see that here we see that we are having C on the almost left side. Okay, and we are having this C on this side, which means the position varies. And if we superimpose these images, if we superimpose these images, we won't be able to superimpose these completely. Okay, because see, if we will superimpose these now, we will see that C is getting over B and B is getting over C, which means that the substance has done some optical activity, and that's why the two structures are not superimposing each other. Okay, so this is how we define the optical active and optically inactive substances. Okay, so let us just move to some examples of geometrical isomers and optical isomers. Okay, see. Now we have to see that how many geometrical isomers and optical isomers are found for the below written octahedral complexes. Now see, these all are octahedral complexes. Okay, and we have to discuss it one by one. As I earlier explained that if we want to know the number of geometrical isomers, we just make different structures of ligands getting attached to the central metal atom. Okay, so this is a Ma6 type geometrical isomer in which we have M as a central metal atom and 6 as a ligand. A6 has a ligand, 6 ligands of same type, that is to say A type. Okay. Now, if we made different structures, different arrangements of this structure, we will come to know that there is only one type of arrangement possible. Now, before we make different arrangements of these given complexes, octahedral complexes, let me just show you one thing, that if any pair has same ligands AA, say AA, okay, we are just talking about the different arrangements that we make for the different complexes, okay, different arrangements for the ligands, okay. So if we get same type of ligands like AA, or if we get two same pairs, okay, then the substance will be surely optically inactive, okay, surely optically inactive. Now, if we see, this is Me6 type, okay. Let me just give you one example of it, like FeF6. Suppose we are talking about this, okay. So this is a substance of type Me6, okay. If we make the different arrangements of it, we will come to know that AA is a repeated, means both are same in it, which from here we can see that this is optical inactive substance, okay. This is optical inactive and there are no geometrical isomers formed. See, if you will make these type of arrangements of the ligands, now you will come to know the number of geometrical isomers and optical isomers, or optical inactive isomers formed of a given complex, okay. So this is Me3B2C type. Similarly, if we made the different arrangement of ligands, we come to know that we find three geometrical isomers in it, okay. Now, for optically inactive isomers, we will see the given condition we have already discussed here, okay. We can see that AA is here, so this is optically inactive, same optically inactive, and both are same optically inactive, okay. And regardless to this, if any another condition comes, then this will be an optically active complex, okay. So this is optically inactive and three geometrical isomers are formed, and you can see that all these complexes are containing monodentate ligands, remember, okay. Now you can see all these with the same concept, that if AA is coming or two repeated pairs are coming, then the substance will be optically inactive. Now let me just discuss one optical active type of case, okay. So this is one Ma3BCD. If we make the different arrangements of it, we get four arrangements, which means the geometrical isomers are 4, okay. So this is another type of case in which there is no AA type of ligand pair obtained, okay, and no AB type or repeated pairs obtained, okay. And if not so, then the substance is optically active. And if the substance is optical active, then we see that the substance will make two isomers, levo and dextro, as we discussed earlier as well, okay. If the substance is optically active, then it will make two type of isomers, dextro and levo. See, there is no such type of case, so this is optically active, and all these have such type of case, so these are optically inactive. In which so we can say that in this complex we have three optically inactive structures, and this structure is optically active, and we have dextro and levo type of isomers for it, which we don't count it as a one complex, okay. We count it as a two complex because this is optically active, okay, that is fine, but it will make two type of isomers further, dextro and levo, okay. So two type of isomers, that are dextro and levo, and in total we count that there are five stereoisomers formed for this compound, okay. And similarly all this you can do. Now let me just give you examples of it. I have already given you example of this, like FeF6, okay. If you see say Ma3B3, we can say NO twice, thrice, NH3. Okay. And so on. You can see that these are just representing ligands and these are just representing central metal atom. So I have just discussed some general forms of octahedral complexes with you, and you can see for several examples. You will find a lot of example in your books. Okay, so I would just like to stop here. This is a special type of case which makes FAC and MER isomers. FAC and MER isomers. Let me just discuss you on another sheet. Okay. So this is Ma3B3 type of complex. Okay. If you see that, this is a very imaginary concept. Like you have to imagine a lot in it. Okay. Octahedral complex having 8 sides. Okay. We have to represent Ma3B3 type of structure in it. Now, if you just see the arrangement of this type, M, arrangement of this type. Okay. See, this type of complex depends upon the triangular structure formed in itself in an octahedral complex. Okay. So if the arrangement is of this type now, then the FAC isomer is formed. So this is the representation for a FAC isomer. Okay. This is a representation of a FAC isomer. And similarly, if you just remove this triangular drawn portion, the portion you will obtain is the representation of MER isomer or meridional isomer. Okay, so if you can see that we just have to make triangles. Okay, the triangle in another phase. Okay, see, these are A and B are the ligands or equatorial lines that are on another plane. Okay, so if the triangle is formed of this type of imaginary like triangle is formed, then we surely say that this is a FAC isomer. Okay, and if the triangular phase while in meridional isomer, we say that ligands are at corners of triangular face. Okay, ligands are at corners of the triangular face. These are corners and ligands are at the corners of the triangular face. This is making a triangle and this makes a MER isomer. See, this is just a different type of octahedral complex which makes FAC and MER type of isomer. You just don't need to go in the imaginary process, because this is just a short type of a little concept in the book of BSc. So if you just remember the general representation of FAC and MER isomer, I think that is much sufficient. Okay, so if we have already discussed the arrangements with monodentate ligands. Okay, now we are just left with bidentate ligands. Okay, you see that AA2, which is two symmetrical bidentate ligands are present. Okay, symmetrical, what does symmetrical refers? Okay, symmetry means if you just make a structure in two halves, you will be able to superimpose, or you will get the two similar two parts of a structure that is being halved. Okay, so if this is a type of complex having bidentate ligand, say of AA type, then we can make two type of structures of it, trans and cis. Okay, and as we know that in this structure the ligands are not on the same plane. Okay, so we can cut it like this. We will cut it like this. Okay, and we will cut it like this because the ligands are on the same plane in this. B and B are on the same plane. Okay, so if we cut it like this, we will see that the two parts that are obtained are superimposable, or the two parts obtained are same. Okay, so if the two parts are same, then there is a plane of symmetry in a complex. Okay, we say like this. And if there is a plane of symmetry in a complex, this complex formed is optically inactive. Okay, and if there is no plane of symmetry, see, if you will cut it like this, you won't be able to superimpose it because these both are in different planes. Okay, and if both are these in different planes, and if you just see it in a 3D way, you won't be able to superimpose this image, and that's why this representation of this complex have no plane of symmetry. And if the complex have no plane of symmetry, then the complex is optically active. And if the complex is optically active, two types of isomers are obtained, dextro and levo. Okay, so we can see that the number of geometrical isomers are 2, as we have already represented. Okay, and the number of stereoisomers are 3. How 3? How 3? The question arises this. Okay, so see, this is an optically active isomer which have two types of further isomers, dextro and levo, and one is optically inactive. And if we have to see the number of stereoisomers, we just include the optical active and optically inactive both type of in stereoisomers. Okay, so two are isomers of optical active and one is in itself and optically inactive. So in total we get 3 isomers. Now there is just an general conclusion for this. See, this is a structure in which B and B are same. See, at this place both are B getting attached to it, means when two opposite groups are same, these are opposite groups which are same, these are opposite positions actually, which are getting the same type of ligand. Okay, and if such type of case comes, then the structure will have the plane of symmetry and the substance will be optically inactive. Okay, so this is just a general conclusion for it. So let me just conclude the things that we have done today. So firstly, we studied the geometrical and optical isomers for coordination compounds. We studied geometrical isomers for tetrahedral complexes. Okay, and we discussed further all examples. See, I have told you many times earlier that these are just general terms. You go through your books and find different examples of it. Some I have already given here. Okay, so this will give you an idea that this is not actually Ma4. This is just a general type of complex which is containing 4 same type of ligands and 1 central metal atom. Okay, and same like this. Okay, then at the next we discuss the optical isomers. Okay, the concept of plane polarized light, dextro and levo type. Okay, optically active and optically inactive substances, we read about this. Okay, and many type of octahedral complexes as well. Then we studied about Fak and Mer type of isomers. Okay, and then we studied about the complexes having bidentate ligands. So this is all about the geometrical and optical isomers for coordination compounds. See, you just have to go through the examples. More the examples you will discuss with yourself now, more you will be able to clear the concepts. Okay, clear the concepts conceptually actually. Okay, you just need to see different type of examples and you will be able to quickly reply what type of isomers is it. Okay, so thank you so much. Hope this video helped you a lot. Thank you so much.